Okay, kiddos, I'm doing this for you to review water. Okay, let's start off with the structure of water. Water has 3 atoms. It has an oxygen atom with 2 hydrogen atoms. Hopefully everybody remembers that much. They are connected to each other by a polar covalent bond. That means they share the electrons between them, but they don't share them equally. Because hydrogen is extremely electronegative, I'm sorry I said that wrong, because oxygen is extremely electronegative, the electrons spend more time around the oxygen, giving the oxygen a partially negative charge. And the electrons spend less time around the hydrogens, giving the hydrogens a partially positive charge. So when you hear about poles, this is what we're talking about, that there's a partially negative end and a partially positive end. These are the 2 poles of the water molecule that makes them act kind of like magnets. Now this bond angle right here is measured at 104.5 degrees. That's not really super important for the purpose of this course, but that is the bond angle of water. Okay. Now, because it is a polar covalent molecule, it can form these wonderful little things called hydrogen bonds. So let's go through and label the charges first. All the oxygen atoms are partially negative. All the hydrogen atoms are partially positive. If you didn't figure it out, this little symbol means partial, okay, as opposed to a full. Because they act kind of like magnets, they attract to each other. So this positive is attracted to this negative, and we draw that with a dotted line because it is a connection and an attractive force. It's not the kind of force where they share electrons. This positive is attracted to this negative. This is what we refer to as a hydrogen bond. I usually just write H bonds. Now, please be careful. The hydrogen bonds are between the molecules, but the polar covalent bonds are within the molecule. So here's your polar covalent bond. Here's a polar covalent bond within the molecule. The hydrogen bonds are between the molecules. Now, hydrogen can make up to 4 hydrogen bonds each. They also can bond with other substances with a hydrogen bond. In this case, it's bonding with the container, and on this side it can bond with the container also. So the hydrogen bonds can be between the water molecules or between the water molecules and something else. That structure in hydrogen bonding leads us to our first series of special properties, and that is adhesion and cohesion. So if we take a look, if this is a penny sitting right here, and this is a water droplet on top of the penny with all these little water molecules, you are going to see adhesion. I'm going to do adhesion in red. Adhesion is where these molecules are attracted to the penny with hydrogen bonds. That's the adhesion portion of this. Now, adhesion is not the only thing going on. We also have cohesion. Cohesion is seen in the middle of this molecule, where all of these water molecules are pulling towards each other. And that's where you see the cohesion the whole way through this. The same is seen over here, where we have a thin tube with some water molecules. The water molecules can adhere to the tube. The water molecules can also cohesively bond to each other with hydrogen bonding. Now, because of adhesion and cohesion, we get 2 specific properties. That water has a very, very high surface tension. That's best seen in this picture up here. These water molecules on the surface, they don't have, the only way they're being pulled by cohesion is into the molecule, into the water droplet. There's no adhesive forces pulling them outward. Because there's no adhesive forces pulling them outward, they're only pulled inward, giving them a nice tight skin across the top. That's surface tension. Over here is capillarity, where water can go up the thin tube, and it can go up a thin tube against gravity. These adhesive bonds keep the water attached to the tube, and if this molecule is pulled up by some force, these cohesive bonds bring all of this column of water with it. And that is what capillarity is, and it has to be a small, thin tube. Okay, on to special properties number 2, high specific heat. This is a hand. It's very well drawn, and this is a droplet of water on the hand. And here is the water droplet on top of the skin, and underneath is the blood vessel. If this has a whole bunch of water molecules, in order to evaporate, we have to break the hydrogen bonds. You need energy to break the hydrogen bonds. So where is that energy going to come from? Well, in this case, this is hot blood coming from the core of the body. As it comes up, the heat energy can be transferred to the water molecules. It can be transferred up. You eventually get enough heat energy to break this hydrogen bond, and this little guy can evaporate. That means there's less heat in the blood, and this is now cooled. This is a thing called evaporative cooling, where water on the surface, and this can be from sweat or it can be from rain, it can be from any source, but water on the surface will take water from the body and cool the blood off. This is good in the summer, it's bad in the winter if you fall into a lake. The same kind of a concept can happen in an ecosystem. The air is gas, obviously, and it changes temperature drastically. Hotter during the day and colder at night without the sun. The water, on the other hand, will hold the heat during the day. It'll bring in the heat from the sun and from the air and hold it during the day, and then it will release it at night. Therefore, this changes temperature much, much more slowly because water has a very high specific heat. This plays a big role in ecosystems. If an ecosystem's dry, it doesn't have this temperature stabilization. If an ecosystem is aquatic or very wet, it can use this temperature stabilization to help the organisms maintain homeostasis. Now, special property number 3. Everywhere will say that water is a universal solvent. That's not completely true, so I don't really like that. But it's true that water does dissolve quite a few different things. So we take a look at these water molecules. We're first going to start off with the small molecules. Okay, small molecules like sodium chloride, salt, which is an ionic compound, will dissolve into these 2 ions in water. Now, because they have full charges on them, these little guys are highly attracted to the water molecule's charges. So this one's attracted to this positive end, the sodium's attracted to the negative end. These guys dissolve very, very well. So ionic compounds tend to dissolve very well in water because these full charges attract to the charges on the water molecules. If you have a small polar molecule, something like ethanol. Ethanol is a carbon-based molecule with an OH on the end. This OH is polar. This is has a negative charge, and it's going to be attracted to this positive charge on this water molecule. It's a partial negative, and it's going to attract to this partial positive. Therefore, this small polar molecule will dissolve easily. Even something like oxygen or carbon dioxide, both of which are non-polar molecules, they don't have any charges on them at all. They are small enough that even though they don't have any attractive forces to the water molecules, they're not attracted at all to these waters. They are small enough that they can find space to squeeze in between the water molecules and dissolve into the liquid. So, to recap, ionic compounds easily dissolve. Polar compounds easily dissolve. Small nonpolars can dissolve, but they don't dissolve as well as the other 2. By the way, oxygen dissolved in water we refer to as dissolved oxygen, or DO2. Okay? That's a critical thing for an aquatic ecosystem to make sure they have enough oxygen to support the animals, and that would be dissolved oxygen in the water system. Now, large molecules are a whole different ballgame with water. This is a long carbohydrate. It's extremely hydrophilic. The water molecules are attracted to it, but they're tiny by comparison to this large molecule. So what will happen is these water molecules will be attracted to it, and it forms what we call a hydration shell, meaning that there's a large amount of water around this molecule. Large polar molecules can sometimes dissolve in water, usually just not in high quantities. Like starch, you can get some starch to dissolve, but not very much. This is a hydrophobic molecule. This is a triglyceride and this baby has no polarity to it. It's completely non-polar, whereas this over here was polar. This is a non-polar molecule, and the water is not attracted to it at all, and it's too large to squeeze in between the molecules. So therefore, the water is actually repelled, and this would separate out from the water completely, and you would get a divisive layer. So this would be something like oil, which would rest on top of the water and would not dissolve in the water. So not soluble, attracted to water, but probably not soluble or not highly soluble if they are large molecules. That leads us to another special case, the amphipathic molecules. Amphi means both, like amphibians live on both land and water. This has both a hydrophilic end and a hydrophobic end. So water is attracted to this side, but not attracted to this. These have a very special property, and if you take a whole bunch of these, they will automatically arrange so that the hydrophobic ends are away from the water molecules, and the hydrophilic ends are outwards towards the water solution. This automatically happens with these types of molecules, so that this hydrophilic end would be on the outside and the hydrophobic end would be on the inside. It just is chemically more favorable and energetically more favorable for this molecule. This also, soap works this way. If your stain that you're trying to wash out is hydrophobic, it will not mix into the water. So if you put in soap, it's amphipathic, this end will attract to the dirt. Woohoo! That's on the stain, and this end will attract to the water, and so then the soap molecule is a facilitator to help the dirt dissolve in the water and therefore be released from the clothing. That is how soap works. Okay. All right. Our last property that I want to talk about here is dissociation. So when we think about water, we think about a beaker with a whole bunch of water molecules. That's only partially true. Some small quantity of those molecules dissociate, which means to not associate, so break apart into the two following things. We have an OH here, that's a negative, and we have a positive hydrogen ion. So the hydroxide is the OH negative, the hydrogen ion is the positive hydrogen ion. This is the same thing as a proton. So if you read something that says it's a proton and you look in the picture and they show H pluses, these two things are the same. So this water molecule has dissociated. You're like, okay, well, great. And it can go back to this format. So we could make this a double-headed arrow. It can go back and forth between these. And you're like, well, how many do this? It's actually like 10 to the negative 7th molecules actually dissociate. It's a very tiny quantity. So, but it's consistent how much water dissociates. So then if we go down here, there's something else that can happen. Because this little guy right here was positive, I'm sorry, that should have been a positive, it can attract to this negative end of the water molecule. And when that happens, it makes this, which is O with 3 H's. That is a hydronium, H3O, and it's a positive because it's picked this up. This is still just a regular old hydroxide ion, like we had up here. This stays the same. This bugger attaches to this guy. And once again, these can fluctuate back and forth. So the molecules can fluctuate back and forth, but it's a relatively consistent amount that are in all these different states when you have pure water, which is what gets us to pH, because you have chemicals that can upset that balance. And so if we're taking a look at pH, here's my pH scale across the top. 7 is neutral, below 7 are my acids, above 7 are my bases. If we take a look right here, I have 2 OHs and 2 hydrogens. I didn't draw the whole water molecules. I just drew the 2 molecules that have dissociated. Right now, I have equal numbers of these 2. If I add a chemical like sodium chloride, which is salt, that will dissociate into sodiums and chlorines. Notice that neither one of these fall into this category. So my OHs, I still have 2 OHs and 2 hydrogen ions, so we're still equal. Therefore, sodium chloride is a neutral chemical. It did not upset my balance. Now, if we come over here to this beaker, if I add something like sodium hydroxide to this beaker, this is going to separate into sodium ions and hydroxide ions. Uh-oh, take a look what happened here. I now have 3 hydroxides and 2 hydrogens. I have more hydroxides than hydrogens. That is what makes something a base. The bigger this difference is, the more basic it is. The closer this is to equal makes it a less basic. Now, here we have this imbalance where OHs are greater than hydrogen ions. So we did that here by adding OHs. We can also do it by subtracting hydrogen ions. So let's take a look at NH3, which is ammonia. It's found in our urine. If I add that to this solution, what it does is joins up with one of these babies and becomes NH4 positive. Well, now that means I have 2 hydroxides and 1 hydrogen left over, so I'm still unbalanced the same way. I still have more hydroxides than hydrogens. These are both bases. Either by adding hydroxides or absorbing out of the solution, this chemical absorbed one of the hydrogens that was available in the solution. Now, if we come over on the other end, we can do the opposite. Okay. If I add hydrogen hydrochloric acid, this is going to turn into hydrogen ions and chlorine ions. Now my balance is off, but it's off in the other direction. I have more, actually I'm going to rewrite that in the other direction. I have more hydrogens than I have hydroxides. This is a strong acid because this happens very readily. If I put this chemical into water, these hydrogens pop off very, very, very readily and makes it extremely acidic. I could do the same thing with another substance, let's just call it X. If I put this in here and it combines with one of these hydroxides, then I will still have more hydrogens than I have hydroxide ions. So both of these would be acids. In bio, we see this scenario in this scenario quite frequently, where we have acids donating hydrogens and we have bases absorbing the hydrogens out of the solution. So that system combo happens quite frequently in bio. Okay, there you go. There's your refresher on water. The end.